So as I said, based on the fault equivalence can be identified that. So if we have a same occurrence of output, okay, based on the test vector, so it should be compared with the test vector also, okay, test vector and the stuck at 0 for A, stuck at 0 for D, and stuck at 0 for J. So based on this occurrence with respect to the test vector, we are going to identify it is said to be equivalent. Okay, equivalent. One set is equivalent. As the same way, next set we can identify G stuck at 1, H stuck at 1, I stuck at 1. So this is said to be one equivalent set. Like this, totally we have a 4 equivalent sets that can be formed throughout this n number of possibilities. Okay, so this so that what happened, we can minimize the number of faulties and identify what will be the output response from this circuit. And here, for example, if within the previous example of the circuit itself, if we have a total of collapsed faulties are said to be 10. Okay, 10 in the sense how we got in the sense. So one number of primary number of output. Okay, primary number of output, one fan out, and 7 gate inputs, and 1 inverter. Okay, 1 inverter. What is the thing in the sense? You can see 1 inverter, 1, 2, 3, 4, 5, 6, 7 inputs are there. Okay, and 1 primary output we have, 1 primary output. Okay, and 1 inverter we have. Fan out, one fan out we have. Okay, 1 fan out we have. So based on this thing, we have a 10 collapsed faulties. So by this relation, 2 into 1 plus 1, you get 4, totally 4 plus this 7 minus 1, you get 6. Okay, so totally for 10 you will be derived over there. So fault collapsing typically reduces the number of stuck at faults by 50 to 60%. So that what happens, you can minimize that. The percentage of reduction is done of faulties from 50 to 60% is reduced over there. The next one comes out with the transistor faults. Okay, so transistor faults. So transistor faults, what happens in the sense, will be representing the transistor faults with the cases of stuck short or stuck open. Okay, so as in the previous gate faults, what happened, we have taken that as in stuck at 1 and stuck at 0. But here in that transistor faults will be representing that as in stuck short or stuck open. So in this also only 2 types of fault is there. Fault types are of 2 only, so k equals to 2. Okay, so here we have an example, okay, which is said to be 2 input CMOS NOR gate. Okay, CMOS NOR gate. So for a stuck short in the sense where the short operation will be done within the transistor of P1 and P2, we have a short operation. Okay, and open in the sense where the one of the transistor is said to be open, where the no connection will be established from the transistor. So in these cases, so based on the possibilities of 2 input 0 0, so we have 2 input 0 0 0 1 1 0 and 1 1, we'll be identifying what is the output of Z or operation. Okay, or operation. But when we come to the cases of stuck at open and stuck at short, okay, so for all the possibilities, so that we can identify the number of faulties can be occurred. So here one stuck at open, stuck at short, stuck at open and stuck at short, and here also N1 and N2 for each and transistor P1, P2, N1 and N2. For all the transistors, we get 2 stuck at open and stuck short, right? So totally 8 possibilities will be defining. So 8 possibilities, 2 into 4, 8, and faulty sites are represented with 4. Okay, 4 faulty sites. So 1, 2, 3, and 4. 4 faulty sites can be represented. So within this 4 faulty sites, what happens when we have our stuck at 0, stuck open or stuck short. Okay, stuck open for the N1, for example, N1 in the sense for this gate. Okay, N channel for the N channel 1. If the transistor is said to be stuck open, this is opened. So when this is open, what happened? There is no connection from A to the N1. So that what happened, A is going to drive an input of 0, and this is going to drive an input of 0 for the first case. When these were going to drive an input 0, 0, this is set to be on. Okay, P channel is set to be on, so that it is going to VDD, it's going to drive an high output logic. You'll be getting as an 1 output. Okay, 1. As the same way, 0, 1, when the stuck at N1 is set to be open, so you'll be getting an output is set to be 0. Okay, as the same way, when we come to the 1, 0, what happens? Okay, 1, 0. 1, 0 in the sense A is set to be 1, right? So this is set to be 1 now. Stuck open in the sense this is opened, right? This is set to be opened. And 0 as an input, 1, 0 in the sense 0 will be as an input for the B. So when it is 0, what happened? This is set to be on. Okay, this is set to be on, and this is set to be off. So when this is set to be on, it is going to drive an some few amount of logic to the Z output, right? Z output. So when it is set to be Z over here, at the output side, what happened? It is going to drive the last value. What is this last Z in the sense? It is going to drive the, what is the last previous logic of value? It is going to drive the last value as a same thing. So it replaces the, it regains the last value. The previous value of the output can be regained at the 1, 0 logic. Okay, how in the sense? So when this is set to be opened, okay, when it is set to be open, the no input will be derived from A to N1, right? It is set to be open now. But B is set to be logic 1, so that B will be driving this logic 1. 1 is there, this is going to drive, N2 will be driving it. And the 1, when it is, sorry, it is 0 here, I'm sorry. So when it is 0, when B is equals to 1, 0, so A equals to 1 and B equals to 0. So A equals to 1 in the sense P1 will be off. Okay, when it is 1 here, it is set to be off. And when it is 0, this is set to be on. Okay, P1, P2 is set to be on. So when it is 0, what happens? This is off, N2 is off, but P2 will be on. So that what happens? The Z will be driving the previous value itself. Okay, previous value. The output will be driving the previous value from P2 to Z. Okay, and this will be opened, so that we will be defining last Z. And finally 1, 1 in the sense both are set to be 1, 1, both are set to be off, so that no output will be defined. We'll be getting a logic 0. Okay, same thing when we come for stuck at short. Okay, stuck at short. Stuck at short in the sense, so when N1 is set to be shorted, okay, when this is set to be shorted. So when this is set to be shorted, what happened? Based on the input logic 0 and 0. So 0, 0 in the sense both are set to be on, and it is going to drive the output is set to be high. But when this is set to be shorted, what happened? It is going to drive some amount of current is derived from this logic. Okay, N1 transistor. Okay, that is what set to be as a quiescent current. Okay, quiescent current with respect to the quiescent value. Okay, quiescent value, that is going to derive it. So that depends, the output will be depending upon the quiescent current value. So that when the N1 is stuck at 1, so it will be derived from the quiescent current. Okay, so that is what IDDQ. Okay, so that is what we will be defining at the output of 0, 0, and remaining will be as usually it is of 0, 0, 0. Same for N2 stuck at open. N2 is stuck open. Open in the sense what happened? You'll be defining with open 0, 0 in the sense they'll be getting 1, 0, 1 in the sense 0, 1, 0 in the sense this is 1. P1 will be on, and 1 in the sense P2 will be off. Okay, P2 will be off. So that what happened? It is going to depend upon the N channel now. N channel, what happened? This is going to drive on 0, 0 here. No flow of current or output will be derived here. N2, what happened? N2 will be driving an last value of a output. Okay, why? Because it is 1 here. If it is 1, what happened? This is going to drive an last output value. So last output of a Z. And remaining are 0, 0, and so on. So like this, for all the possibilities of N channel and the P channel stuck at open and stuck at short can be defined. And here we have the small same representation, same points to be noted here. If A equals to 1 and B equals to 0, the keys of N1 stack open, then output is stored with the previous value of Z only. Okay. If the same thing, if N1 short, then the current flows through the quiescent current, IDDQ. That is what, if N1 is said to be short, that is going to drive an quiescent current as an output. So that will be discussed in the further quiescent current, how the relation is done. So totally up to here, we have discussed with the fault transistor faulties. Now the transistor faulties will be representing with the collapsed fault. Okay, collapsed faults. What were the relation in the sense? So the collapsed faults comes out with equation 2 into T minus of TS plus GS minus TP plus GP. So T will be representing the number of transistors in the circuit, and the TS is number of series transistors, or how many number of series transistors we have, and number of group series transistors in the circuit, and total parallel transistors in the circuit, and group parallel transistors in the circuit, GP. So number of group parallel transistors in the circuit. So totally on this previous circuit, what happened? We have a total of 4 transistors. Okay, 4 transistors and 2 series transistors. 2 series transistors, P1 and P2. Okay, parallel transistors are of 2. Okay, 2 parallel transistors and 1 group series transistor. Okay, and we will be defining with a parallel transistor, group of parallel transistors of 1. So totally we will be defining on the relation with this equation, we will be getting of 6 over there. And the reduction of within the transistor faulties is done by 25% to 35% will be reduced in the faulties.